Classification of matter. First off, when we're talking about chemistry, we're talking about things that have mass, that are matter. It's the interaction of matter. So what is matter? Matter is anything that has mass. In other words, you can weigh it. Now, out of matter, we have these things called pure substances. Now, pure just means there's only one thing. Now, out of those things, though, you can have two kinds of pure substances because it's just not enough to say that it's the only thing in there. We have what's called elements. And when we were looking at the periodic table earlier, I pointed out that an element is anything that's on the periodic table. But what makes an element special is it cannot be broken down into something simpler. And this is something that is often forgotten, cannot be broken down into something simpler, such as, if you have gold atoms or gold elements, you can't break it down to anything else. It's just gold. If you have lead, you can't break it down to anything else. It's an element. And the thing that makes an element special, besides being on the periodic table, is that you cannot break them down to simpler things. Now, that's different from the other kind of pure substance, which is a compound. Now, a compound is composed of more than one element. It is made from two or more elements. Okay? Now, if it's made from two or more elements and it has constant proportion, which means it's the same compound throughout, that means it can be broken down. So it can be broken down. Now, what's an example of a compound? Well, water, H2O. You can break that down to the hydrogen atoms and oxygen atoms. You have salt, which is sodium chloride. You can break that down to sodium and chlorine. An element, on the other hand, is something like maybe copper or hydrogen or oxygen or sodium. They're individual atoms and you can't break them down. But if you look at a compound, it can be broken down. So that's what makes the difference between element and compound is elements cannot be broken down, compounds can. But at any rate, they're both pure substances in that if you have a sample of salt, all you have in there is sodium chloride. There's nothing else. If you have a sample of gold, well, if it's pure gold, there's nothing else in there other than the gold. Now, that's different from what most things in this world are, is a mixture. Now, a mixture has more than one thing. Now, don't confuse this with a compound. A compound is a molecule or a ionic substance, and it's the only thing that's in there. A mixture, on the other thing, is like air. The very air you're breathing is a mixture. It has nitrogen gas, it has oxygen gas, it has argon in there, a little bit of CO2, a little bit of water vapor. Now, out of mixtures, you have two kinds of mixtures. You have homogeneous, and you have heterogeneous. And the difference between the two is homo means same and hetero means different. And so homogeneous means it's the same throughout. Air is a great example. Air is a homogeneous mixture, the very air that you're breathing. Salt water. If you take a sample of air or salt water, it's the same everywhere. The air in my office is the same as the air in the classroom, is the same as the air outside. It's the same everywhere. Same with salt water. If you have a sample of salt water in a cup, it's the same on the bottom as it is on the top, as long as the salt's completely dissolved. Now, heterogeneous means different, depending on where you look at it. Usually, with a heterogeneous mixture, you can actually see, if you look close enough, that it's not the same all the way around. An example of heterogeneous would be like soil. If you go outside and you pull up a sample of soil, it's not the same throughout. You got little pieces, well, around here, you got little pieces of sand in there, and you got little pieces of dirt, and maybe a bug or root or leaf or something like that, but it's definitely not the same throughout. Salad dressing, like Italian salad dressing. If you look at salad dressing, even if you shake it up, you get little particles of oil droplets. But the oil droplets are not the same as the spices, which is not the same as the oil. Vinegar water, it's different throughout. And so the thing to keep in mind, though, is that with mixtures, you got to be careful. Like I said, if you have a pure substance, it can be a molecule which has different atoms, but it's all of the same molecule. Whereas mixtures have more than one thing in there. Like salt water, it has salt and it has water. Air, it has nitrogen molecules, oxygen molecules, argon atoms, and so forth. And salad dressing, of course, is a mixture of a bunch of different things, but it's not heterogeneous. I mean, it's not homogeneous in the sense that you have to shake the salad dressing before you can put it on your salad. Okay, so that's classification of matter. Now, when we have matter, they can have different states. States of matter. And there are three kinds of states of matter. You can have solid, you can have liquid, and it can be a gas. Now, some people will say, well, what about plasma? Depending on who you talk to, plasma may or may not be a fourth state of matter. Generally speaking, plasma, from a physical standpoint, is an ionized gas. So it's still a gas, it's just ionized. And so solids, liquid, and gases have different properties that go with them. Before I go on there, solids and liquids are also known as the condensed phase. Condensed. All right, they're called condensed because they're condensed together, and gases are very far apart. And so, what sets apart solids, liquids, and gases of each other is the particles. They all have particles. Solid particles are generally have a fixed position. In other words, once they're where they're at, the atoms or molecules that comprise a solid, once where they're at, they don't move. They don't move around. I mean, they do kind of wiggle in place, but on average, they stay in a fixed position. Liquids, on the other hand, their particles are able to move randomly about. They move randomly. Okay. Now, they are, however, close together. Both solids and liquids is distance in between. Let me write that out. Now, we have to make sure that we understand that solids have fixed positions, but they're very close to each other. And liquids are also very close, but maybe not quite as close. So I will just say they're close together. So solids have fixed positions and they're very close together, and liquids move randomly about. That's how they flow, and they're still close to each other. Now, gases are very different from solids and liquids. The first thing is that they are very far apart. As a matter of fact, they're so far apart, you say far apart from each other. And not only are they far apart from each other, but they also move randomly about. Similar to liquids, but with much larger distances between the individual gas particles. So gases move randomly, just like liquids move randomly. But unlike solids and liquids, they're very far apart, far, far apart. And so they're allowed to go in straight lines for quite some distance before they run into each other. Okay, so if we look at some other characteristics like the volume, well, solids, if you look at the volume of a solid, like so if you pick up your cell phone, well, that is whatever the volume of that cell phone is not going to change no matter what you do to it. You put it in a box, put it in your pocket, whatever, the volume doesn't change. And when we say that the volume doesn't change, we say it has a fixed volume. And the same thing with liquids. If you pour, say, from a coffee pot into a coffee mug, the volume doesn't change. So we also say that the volume of liquids is fixed as well. Now, gases are very different in that respect. The volume of a gas depends on the container that it's in. So if I pump air from this room into a tire, I'm changing the volume of that air into the volume of the tire. So it takes the volume of the container. Okay, and finally, let's look at the shape. And so a solid, like I said, with a calculator, not only is volume, or with a phone or whatever solid, not only is its volume whatever it is, but its shape stays the same. So your calculator is still calculator shaped, no matter what you do to it. Your cell phone is still cell phone shaped, no matter what you do to it. Liquids, on the other hand, if you pour it from one container to the next, if you say pour from a from a coffee pot into a coffee mug, well, it goes from being coffee pot shaped to mug shaped. Now the volume doesn't change, but the shape does. So we will say that the shape of a liquid, it takes the shape of the container. Now it takes the shape of the container, but the volume doesn't change. Now gas also takes the shape of the container, but the volume is what the container is too. And so it takes the shape of the container. Let me put the shape in here. Takes shape of the container. But it also, because it takes the volume of the container, it fills the container. No matter what the shape is, no matter what the volume is going to fill the container. And that's different from a liquid. A liquid does take the shape of the container, but it doesn't necessarily fill up the container. You can fill a glass halfway. But if you were to put gas into a glass, it will fill up the entire container of the glass. All right, so that's our states of matter. So we have three kinds of states of matter. We have solids, liquids, and gases, and they have some characteristics which we need to keep in mind about them. Okay, now another characteristic of matter is we have something called temperature. Now this is usually it's how cold or hot something is. But really, it's a measure of what's called internal kinetic energy. And what I mean by that is that atoms and molecules are constantly moving. And kinetic energy is the energy of motion, and it's the ability to do work. And so as you heat up things, well, the atoms and molecules, they wiggle around more. So they're constantly moving and wiggling. And as you heat up things, they wiggle more. And as you cool down things, they wiggle less. Now, solids will stay put and liquids will move around, and gases will just go even faster. So it's a measure of internal kinetic energy. And generally, the way we measure temperatures, we use something called a thermometer. Okay, now there are three temperature scales commonly used. Now there's many more temperature scales than just the three that I'm about to cover here. And one of the first temperature scales was something called degrees Fahrenheit. Now, the temperature scale of Fahrenheit is based on properties of water, specifically the freezing point of water and the boiling point of water. And Fahrenheit, who was a person, a real person, he set the freezing point of water, he set at 32 degrees Fahrenheit. And he set the boiling point of water at 212 degrees Fahrenheit. And in between these, from 212 to 32 degrees Fahrenheit, we have 180 degrees in between. 32 from 212 gives you 180. Okay, now, why he picked 32 for the freezing point and 212 for the boiling point, I don't know, but I suspect he picked 180 degrees between them because that's half of a circle being 360 degrees. Now, fast forward a little bit in time, and we have this person called Celsius. And he says, well, you know what? We're doing the metric system. This was when the metric system was coming out. The metric system is based on powers of 10. Well, why don't we set up a system for temperature that is based on the powers of 10? So he says, you know what? We're still going to use the freezing point of water, except we're going to say freezing point of water is 0 degrees Celsius. And we're still going to use the boiling point of water, except now we're going to say the boiling point of water is 100 degrees Celsius. Now, part of the beauty of this is it's easy to remember 0 and it's easy to remember 100. 32 and 212, well, some of you may have known that already. That's freezing point and boiling point in Fahrenheit. But Celsius said 0 to 100, and now 0 to 100, we have 100 degrees in between. So this becomes a metric temperature scale. Now, it does have problems, though. You can have negative temperatures in degrees Celsius. You can also have negative temperatures in degrees Fahrenheit. You may have remembered a couple of winters ago when it was below 0 outside, and it was below 0 on the Celsius scale. And you may say to yourself, why does it matter that I can have negative numbers down here? Well, it causes problems when we want to do calculations that involve temperature. And if you have a negative temperature, you're going to get a result that may be negative. And so in particular with gas law calculations, which we'll do later, you can end up with really strange results like negative volumes and negative temperatures. You can't have a negative volume. You either have a volume or you don't. You can't have less than that. And so to fix that problem, another fellow came along called Kelvin, and he devised a temperature scale that was based on gases. And he says, you know what, there's a point where things can't get any colder than cold. And we're going to say, not based on water anymore, we're going to say way down at minus 273 degrees Celsius, really below 0, we're going to call that 0 Kelvin. And since you have no more kinetic energy at 0 Kelvin, we're going to call that absolute 0, because you absolutely cannot be colder than 0 Kelvin. Do not confuse that with 0 Celsius. 0 Celsius is way warmer than 0 Kelvin. 0 Celsius is the freezing point of water. 0 Kelvin is absolute 0. Do not get those confused. And to keep it metric, what we've done is we keep the same spacing for Kelvin, so that if you have 0 degrees Celsius, we're going to say that's 273 Kelvin. And we're going to say 100 degrees Celsius, since we're keeping the same spacing, that would be 100 Kelvin more. That would be 373 Kelvin. And we have in between, well, 273 from 373 is still 100. So you have 100 degrees Kelvin between 273 and 373. So it's still metric, but now we're not basing Kelvin on anything other than absolute 0 and keeping the spacings the same. So it's not based on any physical property other than that's the point where the atoms and molecules stop moving. You've taken out enough energy where that happens. So whatever you do, do not confuse 0 degrees Celsius with 0 Kelvin. They are not the same thing. Now, we have to be able to get between the different temperature scales, and this you need a conversion factor for them all, and you can either memorize it or put it on flashcards. But the way it works is like this: it's degrees Celsius. If we want to go from Fahrenheit, we would say 5 nights. We would say degrees Fahrenheit minus 32 divided by 1.80. And what's happening here is we're taking the Fahrenheit. If we subtract off 32, we get back our 0 going to Celsius. And the 1.8 comes from the fact that you have 180 degrees Fahrenheit for every 100 degrees Celsius. And if you do that, you get 1.80. And that's where the 1.80 comes from. So this is how you go from degrees Fahrenheit to degrees Celsius. You plug in your number, make sure you hit either equals on your calculator. In other words, Fahrenheit minus 32, hit equals, and then divide by 1.80, or make sure you put it in parentheses. And to go back to Fahrenheit from Celsius, what we do is we say 1.80 times degrees Celsius. That gets us back with the right scale. And then to go back, we have to add the 32 back in. And so we can go back and forth between degrees Celsius by plugging and chugging with our numbers here. And finally, we need to be able to get to degrees Kelvin from Celsius. And as you can see here, to go from 0 to 273, well, you just add 273. This is how you get Kelvin. And strictly speaking, it's 273.15, but usually we just say 273. And to go back in the other direction, well, if you add in one direction, then you must subtract in the other direction, and that's minus 273.15. Keep in mind that when you're going from Kelvin to degrees Celsius, you can get a negative degrees Celsius if you're sufficiently cold with your Kelvin, but the Kelvin's always going to be positive. Okay, so we can do some calculations with this, and we can go back and forth. And let's say we have someone who is running a temperature. Let's say a child has a temperature of 104 degrees Fahrenheit, and I want to know how many degrees Celsius is that. And so we would take the 104 degrees Fahrenheit, we would subtract off 32, and then divide by 1.80. And we do that, and we put that in our calculator, because nowhere else in the world do we use degrees Fahrenheit except for here in the United States. So we subtract off 32 and divide by 1.8, and I get a 40.0 degrees Celsius temperature. Now I wonder what a normal temperature is. Normal temperature is what, 98.6. Let's see what normal is. And we divide by 1.80, and 98.6 minus 32 divided by 1.8, and let's see, 98.6. And I get 37 degrees Celsius. Now we can also go back in the other direction as well. We can say, if a person has a temperature of, say, 35 degrees Celsius, which means they might be running a little cold or hypothermic, well, we can also do that. We can say times 1.80 plus 32. And we can see what temperature that is in Fahrenheit. And that's a temperature of 95.0. So that person is probably pretty chilly. And as long as you have the formulas in front of you, all you have to do is just plug in the numbers. And so we can also take that 37 degrees Celsius, and we can go to Kelvin. And to do that, I would just add 273 to it, and we can say 37 plus 273, and you get 310 Kelvin. And we can also convert from Kelvin. Let's say if we had 205 Kelvin, and I want to go to degrees Celsius, well, then I would subtract off 273, and I'd get 205 minus 273, which would give you a chilly minus 68 degrees Celsius. So that's how you convert back and forth between the different temperature scales, is you have these four conversions over here: Celsius to Fahrenheit, Fahrenheit to Celsius, and then Kelvin to Celsius, and Celsius to Kelvin. And if you want to go from Fahrenheit to Kelvin, what you would do is you would convert Fahrenheit to Celsius first, and then go from Celsius to Kelvin. So you would have a two-step process to do that.